Hi, my name is Dan Fenter, student number 64360172, and this is for my design project 3, and today I'll be presenting my wind speed logo.
The user requirements I selected is the user needs to be able to view the speed of the system anywhere in the world via the internet. The system must be able to accurately log speeds between 5 and 35 meters per second. The system needs to be battery operated to make it easy to install, and the wind speeds must be visible from a browser. Ideally, the system should be waterproof to work in outdoor conditions, since it will primarily be an outdoor device. For the conceptual design, the electronic conceptual design, we can see that the device is powered by a solar panel. This is, however, not the only way it needs to be powered, since there isn't direct sunlight the whole day. It then goes to a lithium-ion battery charging circuit, which charges a lithium-ion battery pack, which then goes to a buck-boost converter, which powers the rest of the circuit. Here's my detailed engineering design. This is my schematic. As you can see, there's a battery charge circuit, there's a buck-boost converter, here's all the power connections, all the add-on schematics, so there's a push button for future use, there's 4 status LEDs, there's an ESP32 microcontroller, and there's 4 Hall effect sensors. Here you can see the board layout, which I designed. This was manufactured in China due to the low cost. Here you can see my mechanical design. So the base of the design is created with an FDM 3D printer, so fused deposition modeling. And this section over here is acrylic, which has been laser cut. Next we go to simulation. There were no simulations that were done in the schematic. When we go to project implementation, we can see here the boards that I received from China. They came out perfectly, and I placed solder paste with a hand solder paste machine. The components were then placed on the board, and the board was reflowed with a hot air station. Here we can see the mechanical components, mechanical components which have been placed on the 3D printer, and here you can see the parts after they've been removed. The rest of the parts were then assembled, and here you can see the final assembled product. Okay, so the most critical part of this is viewing data accurately. So here you can see real-time stats of the device from a website which I created. I used Flutter, which is an app development framework, since I'm comfortable with it. Next, we go to the test procedure and functionality. Here's me testing the buck-boost converter. As you can see, I'm probing the 3.3 volt and ground line on this circuit. I got a 251 millivolt ripple, which is quite high. It's something that could be improved upon. And then 3.39 volt output. Here we can see the solar charge tests being done. I'm probing the battery input, since the charge controller charges the battery at different currents based on the battery's current voltage. And I got a 188 millivolt ripple voltage and a 3.83 volt output voltage at this stage, which means the battery was at 3.83 volts. Here we can see the solar test results. For the on the left, we can see the battery voltage when it's placed in direct sunlight, and on the right, we can see the battery voltage dropping when it's not placed in direct sunlight. The calculations were done so that the battery could be charged and the circuit can operate at the 5-watt panel's output. This means the battery will charge, and overnight it would be able to work. Okay, for the wind speed tests. For the wind speed, I needed a way to generate wind speeds which are known to me in order to calibrate the device. So I derived a formula based on the dimensions of the test jig that I designed. And from there, we can see over here, this is the formula that was derived, or one of the formulas that were derived. And in order to do the tests, I increased the output pressure of an air compressor in 100 kilopascal increments, which generated a wind which was known, and the data was logged on a Google Sheets document. And from here, from the results that I gathered, the K value of the system was found to be 2.2, which was later on used to convert the frequency of the system into an actual wind speed in meters per second. Okay, for the problems that I encountered a big issue with the Hall effect sensors, which I initially thought was a firmware issue, and then later on discovered that the pinout that I had used on the board was swapped around on the SOT23 package. This was resolved by soldering the component on, as you can see in this image. After that was resolved, I was unable to measure high wind speeds, and I started looking closer into the data sheet of the Hall effect sensor that I selected. I then saw that the response time of the Hall effect sensor is relatively slow. It was too slow for my application, so I swapped it out with a different Hall effect sensor which had a much faster response time, and the issue was resolved. For the budget, I spent 306 Rand on components, 335 Rand on manufacturing, and 290 Rand on the test jig. Here we can see the assembly of the device. Whilst designing the device, the assembly was something that was considered and was therefore made as easy as possible. First, we insert the battery connector. Next, the following sub-assembly is attached to the rest of the system. First, the solar panel is plugged into its designated area. On the board, the solar panel and battery connectors have been labeled. This is for testing purposes and for ease of assembly purposes. The connectors also have different sizes to prevent anyone from assembling this incorrectly. Next, the perspex part is placed to the FDM part and all the screws are fastened. Here we can see the device working under relatively windy conditions. Here we can see the Google Sheets document where the data is stored, which is later viewed by the front-end software.